Let's look at LRU Cache. Design and implement a data structure for least recently used cache. It should support the following operations: get and put. Get of key. Get the value will always be positive of the key if the key exists in the cache. Otherwise return -1. Put of key comma value. Set or insert the value if the key is not already present. When the cache reached its capacity, it should invalidate the least recently used item before inserting a new item. Could you do both operations in O of 1 time complexity? Now, in order to achieve the get functionality in O of 1, we might have to use a hash map. And in order to achieve the put functionality in O of 1, we might design a data structure in such a way that we use a linked list. But in order to also ensure that we invalidate the least recently used item before adding a new item, we might design a data structure such that the least recently used node would be at the end of our linked list. But in order to invalidate that in O of 1, we might need the reference to the node before the last node. Hence, there is a need to use double linked list instead of a single linked list. Now, assuming that we use double linked list with the least recently used node at the tail end of the data structure, we can go through the example to understand how LRU cache would work. Initially, with 1 as a key, value 1 is added, and with 2 as a key, value 2 is added. So at this stage, since 2 is added as the latest, so 2 goes at the head and 1 is at the tail. So again, when you try to get 1, 1 goes at the head and 2 becomes a tail. So when you again add 3, you have to evict the least recently used, which in this case is 2. So when we try to get 2, it returns -1 since 2 has been already evicted. Now keep in mind adding 3 moves it to head. So right now 3 is at head and 1 is at tail. So when you try to add 4, 4 is added to the head, 3 becomes the tail and 1 is evicted. Therefore when you try to get 1, it returns -1. When you get 3, 3 is again moved to head, and when you get 4, 4 is again moved to head. Now since in order to evict once the capacity is reached, we might need to have a running variable that would measure the current size, besides having another variable capacity that would be instantiated when we initialize the LRU cache. So let's go ahead and declare private current size to keep track of the current size, and max capacity key to initialize the LRU cache. Now, in order to define a data structure that would function as a doubly linked list, let's go ahead and define class node with private members as key and value. Besides that, we'll also define node previous and next in order to function as double linked list. Let's go ahead and declare default constructor as well as parameterized constructor to initialize a key and value. Let's initialize previous and next nodes to null. Now in order to get particular node in O of 1, we might have to declare a hash map. Key would be an integer and value would be a node data structure. Let's also initialize start and end to mark the start and end of our double linked list. Map to get in O of 1. Current size to keep track of size. Max capacity allowed for our cache. With that in place, let's go ahead and define the constructor of this class. So we'll store this capacity in max capacity. While initializing current size to 0, we initialize both a start and end of our data structure using a default constructor. Starts next would point to end, and ends previous would point to start. That in place. Now, if the key does not exist in the cache, you have to return -1. So let's go ahead and translate that into code. If the key does not exist, you return -1. If the key exists, we need to return the value present in our node data structure. Therefore, we need to first get the node. And we need to return but before doing that, since we are accessing this particular node, we need to move it to the head since it becomes a most recently used node. So let's invoke a function that we need to define by passing this node as a parameter. Moves the most recently used node to the head. Now, in order to define the put function, we once again check if map already contains the given key. In the condition that it doesn't, we define a node with the given key and value. We check whether the cache is full or not. If it exceeds the capacity, we clear our cache. this would evict the least recently used cache. Once that is done, we have to insert to head the newly created node, most recently used node, new node is in added to head to resemble most recently used node. We also add an entry to the map, the given key, and we increment current size to keep track of whether capacity has been reached or not. Now, if the key does exist, we again get the node and we update that node's value with the new value. And since we access that node, we have to move to head this node. Again, moves to most recently used to the head. With this in place, now we got to go ahead and define these three functions that we created: move to head, insert to head, and clear cache. Let's define move to head. In order to move a particular node to the head, we need to ensure that both the left-hand side and right-hand side connection of the node is re-established so that that particular node can then be freely moved to the head. So before that, let's sanity check whether this node is already at the head position. If the previous of this node points to start, then it's already the head node, so you simply return. Otherwise, you take the previous node's next and assign it to the next of this node. And similarly, you take the next node's previous and assign it to the previous node. With this done, this node can be freely moved to the head. So here we can again call insert to head with this node reference. Next, we go ahead and define insert to head. In order to insert to head, we first define next as the node that is next of start. We establish the right hand side connection between node and the next. So node's next points to next and next previous points to node. Then we establish the left hand side connection to this node. Starts next points to node, node's previous points to start. This way our node is now in between the start and the next node and therefore acts as our head node. With this in place, go ahead and define clear cache. So this method would be invoked when the current size exceeds or equals max capacity. So we'd continue evicting until the current size becomes less than max capacity. If let's do a sanity check where tail.previous is already start. With this means that there are no nodes to be evicted. So simply return. Otherwise, since we define that as end, this is actually end. Otherwise, what you do is you take so end dot previous dot end dot previous is assigned to a tail node. Now tail is our last node and this has to be evicted. So tail dot previous dot next assigned to end and end dot previous is assigned to tail dot previous. After re-establishing the connection, this tail node is free to be evicted. So you can say map.remove tail nodes key. And important to decrement current size so that this loop will terminate. So this way, this seems done. Let's go ahead and run this code. There's a compiler error. So let's remove this access modifier. Let's keep it non-private so that it can be accessed outside this class. Seems to have run here. Let's go ahead and submit this. So this way, time complexity for the get method is O of 1 because we're using a hash map to get the node, and time complexity for put method is O of 1 since we're using a, here it's because of hash map, and here it's because of double linked list. And space complexity would be O of n, where n is your max capacity. Thank you.